Hi guys, how we doing?
Morning, guys.
Mr. Kane here, and
This is Goswish.
All right.
Quantum mechanics.
Quantum mechanics. Yeah, I guess that's it. So yeah,
I used to watch a show called Quantum Leap when I was
go take a quantum
younger.
leap.
Yeah, had the kind of same term.
Yeah.
I don't know. There's not a lot you can say about that line. There's not even a joke.
It just reminds me on Star Trek of a guy in a jumpsuit that crawls under the hood. And all right. So goals for quantum mechanics, guys. We want you to be able to describe the atomic orbitals in size of quantum integers, their shapes, their size, and their energies. And we're going to do that in this video.
Okay, I know the word. I noticed the word is orbitals instead of orbits, so something tells me this is a smidge different than Bohr.
Just a smidge, just a tiny bit.
All right.
But it's a little bit different. We want you guys to be able to apply what's called the Aufbau principle, the Pauli exclusion principle, and Hund's rule to describe the arrangement of the electron within orbitals.
Okay, just one quick comment, Mr. Kane. Electrons, yeah, because when we start getting deeper in the periodic table, it's all of them, correct?
Yeah, this should say electrons because there are more than one electron.
Yeah, when you start getting into that francium and zirconium and stuff, there's more than one, that's for sure. Once
you get into helium, there's more than one.
That's true.
Yeah. Okay. All right, so we also want you to predict the electron configurations, the orbital diagrams, and the noble gas notation.
Okay.
That's not so hard stuff.
No, you just gotta pay attention.
We'll do that eventually. And then finally predict the relationships between the elements using periodic trends.
Okay.
That requires some memorization. We've got the important ones in bold here. Ionization energy, atomic radius, electron affinity, and electronegativity are things that go with us from here on.
Yeah.
But we'll also talk about how ionic radius and melting point can be predicted on the periodic table.
All right. Sounds like we're going to need a periodic table in front of us. All right, 1970 to 1924. So this is still kind of a history lesson, like we've been doing all along. Tried to make the Bohr's model work for all the elements, not just hydrogen. Please remember, we keep calling it the Bohr model of the hydrogen atom.
Right, yeah, and there's a reason for that. Back then they didn't call the Bohr model the hydrogen atom because Bohr didn't know that it was only going to work for hydrogen.
Hydrogen, yeah.
And he was trying to get it to work along with a whole bunch of other atomic scientists and physicists.
Yeah. Oh, I mentioned de Broglie.
Did you?
Yeah, because he's the guy who said that everything kind of vibrates, even matter. So he's the one who kind of put matter into the wave categories too.
Yeah. Okay. So he's French by name, right?
Yep.
And he suggested that the Bohr model has electrons that appear like particles, kind of like what you just said. Okay. So particles behave like they're waves.
Right.
And that's exactly what he said. And they continued on that and found that electrons scattered in a diffraction pattern, which means that they are actually waves.
Yeah.
They behave as waves, just like light does. And de Broglie applied a wave theory to Bohr's model of the atom. So he applied some wave mechanics, some actual wave mathematics. The energy levels of Bohr's model now turn out to be wave patterns.
Schrodinger. Schrodinger's cat. He's the guy who's actually, it's his theory. They call it the Schrodinger quantum mechanical theory.
Because he did the final.
Right. Yeah. I thought he was the one who called them orbitals, but whatever.
Okay, maybe I was wrong there.
He's the theory we use to this day.
Okay. He did some complicated math.
Oh, he did some nasty differential equation calculus math.
Differential equation? These are sophomores. Do they know differential equations yet?
No.
Should we teach them differential?
No.
Okay. All right. We won't teach them that. All right. So ultimately, guys, it's complex math. We're not going to get into the actual math part, but we will get into the results of what the math are, right?
Correct. Yeah.
Okay. And the results are something we call the Electron Cloud or the quantum mechanical model.
Yeah, it's got a couple of different names. Schrodinger's model, quantum mechanical model, wave model. It's got a couple of different names.
All right. There's the math.
Yeah, it's ugly.
Should we stay on this page for long?
No.
Okay, here we go. Going on. All right, so basically, the math that we just showed you shows the probability of finding an electron at a given time and place. We should actually have the word and place here.
It's kind of like a statistics, right?
Right. It's a little bit of statistics. Yeah. And because it's giving you time and place, you can graph this. It's giving you x, y, and z coordinates.
Right, it's three-dimensional.
So you can get a picture of what the electron cloud looks like.
It kind of looks like, well, that's a real colorful picture, but usually it just kind of looks like what I call like a dot diagram,
Mm-hmm.
like an MRI or something like that.
You can see all these tiny little blue dots.
Yeah.
Every single tiny little blue dot is just a place where there's a prediction that an electron might be at a given point in time.
Yeah.
And this is the atom in its ground states over here on the left. So that's a hydrogen atom in its ground state, because notice there's only one proton. And notice that the electrons are in a cloud. It's kind of fuzzy. Where's the electron? Where's the probability of an electron being end?
In that circular thing,
Yeah,
90% of the chance being in the circular, because humans put a circle on it.
Right, exactly. We see that as a sphere, but it's kind of fuzzy at the edges. I think that's why they call it a cloud, because clouds are fuzzy. Now, the reason why there's two pictures here is because this is the excited state, so if you get the electron in a higher energy level...
Right, it's going to be bigger. Bigger and further from the nucleus.
Schrodinger didn't say that energy levels were gone, did he?
Nope.
No, he just described something called an orbital, which we're getting to.
Right. They're no longer orbits like in the Bohr model. Now they're called orbitals because they're statistical probabilities, and Bohr thought it was a perfect concentric ring, and Schrodinger said, no, it's not. It's a probability. It's a darkened spot on like an X-ray kind of a thing, where they think the electron is got a 90% chance of being.
Okay, so 90% was the number? Is that an important number?
That's an important number. Ooh. Models.
What are these models of?
These models are of the probability maps that are available to us for the Schrodinger wave equation.
So they're not all spheres?
Nope, not all spheres. And they're all three-dimensional, that's for sure, and they all have the potential of sitting on all three axes.
Huh. Here's another question.
They have more letter designations than anything, S, P, D, and Fs.
So this is an S?
Yeah.
And then these three guys that are in the next row, I'm assuming that they're all together for a reason.
Yeah, they're all together in the same row. Those are Ps.
Those are Ps, okay. And then these guys in the next row look like they all belong together also, so they are
Ds.
Ds, okay. And then these guys in the next row are
Fs.
Fs, okay, all right. So there's one S, there's three Ps,
right.
There's 5 Ds, and there's 7 Fs. Wow, that's a lot. Okay.
And they go on further than that, Mr. Kane, but we only go up to F because it correlates to the periodic table.
Oh, that's right. There are S, P, D, and F blocks on the periodic table.
Yep.
I think we've talked about that in class.
Yep, we have.
All right. All right. So it turns out that with better spectroscopes than we have in class,
right,
you don't see just one line for each of those colors of hydrogen. So there's not just one line of purple.
And this is where Bohr models started falling apart.
If you can take a magnifying glass on the purple line, you can actually see several lines there,
yeah,
right?
And I think the red one turned out to be 3 different lines.
So what we find out is that electrons aren't bound just in these circular orbits that Bohr had talked about, but that they can live in these orbitals that are in Schrodinger's model of the atom. There are some rules here. Each energy level can wind up having one or more orbitals. And each orbital can hold up to 2 electrons.
Right, which is the Pauli exclusion principle.
The scientists actually described those lines that they saw as sharp, principal, diffuse, and fundamental. So that's why they named it S, P, T, and F, which is why we've got an S, P, D, and F block on the periodic table.
S, P, D, and F, they're all orbitals that have different shapes.
Right, which is what we saw on that slide before. And some of them have multiple types of shapes. Orbitals of different energy levels have different sizes. So an orbital of the first energy level is small, and an orbital of the second energy level is
larger. All right, so here's an S orbital.
And it's kind of nice. S, spherically shaped. That wasn't necessarily done on purpose, but it's a sphere.
Notice that it's a 3-dimensional. It lies on all 3 axes.
Right, X, Y, and Z.
So there's only one orbital to the S.
Just that one sphere shaped.
Yep, 2 electrons maximum.
Okay, so I can put 2 electrons in here.
Right, you can also put 1 depending on what substance it is, but I mean at maximum 2 electrons.
I can put up to 2. All right,
up to 2.
2 that's why it says 2 electrons max there. If I had a 1s orbital, it might be small.
Right, and 2s would...
An s orbital of the second energy level would be larger.
Right, because it's spherical in shape too, because humans put a defined edge onto the probability map.
Right.
Remember, this is basically the probability map with a defined edge on it, and it came out to look spherical in 3 dimensions.
Right.
So each successive s orbital for a higher energy level will be bigger and bigger and bigger and bigger.
But they'll all be spherically shaped.
And they'll all be spherically shaped.
Then there's the p orbital. The p orbital's dumbbell shaped, which this looks like a dumbbell, doesn't it?
Right.
And this looks like a dumbbell.
Right.
And this looks like a dumbbell. It looks to me like, according to this picture, there's just 3 different dumbbells in different directions. One on the x, one on the y, and one on the z.
Yep.
And is this what it looks like if I put all
together.
3 together at once?
Yep, pretty picture.
So because we can have 3 orbitals, they can combine together. That kind of looks like balloon art.
Yeah, really. Yep, it does. All right, so let's see. The p orbitals then can only have 3 orbitals.
Okay, so the x, the y, and the z?
The z, yep.
Okay. 2 electrons per orbital. So I can hold 2 in the x, 2 in the y, and 2 in the z. That's a total of?
6 total.
That's a total
Maximum
of 6.
of 6.
Okay. So maximum of 6.
Not as pretty as a picture as the other one.
Yeah, it's a little bit different. It's not as colorful.
All right, so d orbitals are going to have 5 orbitals. What I see on the picture is basically 4 cloverleafs and my particular favorite, the dumbbell with the donut, which you call a dumbbell with a torus, which torus to me is my car.
Yeah, okay. Let's look at the 4 that are similar first. This one, the second, the third, the fourth, and the fifth all look like cloverleafs?
Cloverleafs to me, yeah.
I see that. Some people call them double dumbbells because there's a dumbbell here and a dumbbell there.
Yeah.
Do I have to memorize these specific shapes, or can I just memorize the fact that they're double dumbbell cloverleafs?
Double dumbbell or cloverleafs, and the last one donut.
I'm not going to have to draw it.
No, because we're not very good artists, that's for sure.
All right, so I just have to worry about the fact that they're double dumbbell cloverleafs, or that they're dumbbell torus or dumbbell donuts.
Yeah.
Okay. All right. There's 5 orbitals.
5 orbitals. Yep. 2 each. 2 electrons each. Beg your pardon.
Maximum. Right.
Maximum.
So I could hold up to 10 electrons. So let me get this straight. S, there's 1 orbital.
Correct.
P, there's 3.
Correct.
Z, there's 5.
Yep.
So far, we're using odd numbers.
Yes.
1, 3, 5.
Yep.
So if there's another type of orbital, how many could there be?
Well, let's see. What did we say? 1, 3, 5. I'm going with 7.
All right, let's check it out. F.
7
orbitals.
Oh, those are ugly.
Hey, I liked how we described the shape.
Complex shapes. There you go.
So in other words, don't memorize what the type of shape is.
That one's easy.
They're too complex.
Yeah, we were going okay with the SPD, but man, you get to FGH and stuff, and they're just ugly.
I don't even want to show them the G's.
Yeah, no, the G's are hard. And bleh.
Yeah, G's are difficult.
Yeah.
But just realize that these are complex shapes. Take a look at them for interest's sake. You don't have to draw those out, obviously. But there's 7 orbitals. So if each orbital can hold 2 electrons, we get a total of 14 electrons that can be held.
Yep. And keep in mind, this is from instrumentation that showed, I guess you'd call it what, spectrograph or something like that, dot diagrams that came out with, they called them density maps. And this is what the density maps looked like. And humans put defined edges on them. And when we put the defined edges on them, this is what it looked like to us. That's why we call the other ones spherical, dumbbell with the donut.
So these are just models.
These are just models of what the machine spit out, basically, the instrument spit out.
Oh, hey, quick review. Let's see if we can name these again. That first one is definitely S, right?
Right, 1 orbital
because it's
S.
spherically shaped.
Right.
Now these look to me like they're dumbbells, right?
Yep, those are the 3 P's.
One going up and down,
on the
P,
yeah.
One going
PX,
outside the
PY,
side,
PZ.
and one going in and out. So now there's 2 dumbbells, there's 2 dumbbells, there's 2 dumbbells, there's 2 dumbbells, so those are all D's. So D, 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 and there's the double dumbbell with the donut in it.
Yep.
So another D. Okay.
So you got 4 cloverleafs and the dumbbell with the donut.
So we can check our work here. 1, 3, 5. Okay, the next one's 7, right?
7, yep.
F's. This is an F.